Bachelor of Science in Water Engineering, Master of Science in Water Civil Engineering, and he is a first-year Ph.D. student in the Department of Geography and GeoInformation Sciences, GGS, here at George Mason University, where his dissertation research is focused on precipitation non-stationarity in order to develop innovative methods to adapt civil engineering practices to changing hydrologic conditions. Akko is interested in hydroclimatology, water resources management, stochastic hydrology, and remote sensing. Further, he has extensive experience teaching water resource engineering, managing projects, and working as a professional water engineer. Akko Heidari.
Good afternoon, everyone. Thank you for coming. Today I'm going to talk about an interdisciplinary approach to climate change in order to create a bridge between climate science and civil engineers. Climate change. We almost every day hear about many storms, floods, drought in all around the world. So, there are many questions about climate change, and as we know, here in the United States, there are some climate change deniers and some green activities. We will go further and discuss climate change and water cycle intensification, stationarity is dead, and adapting to the non-stationarity world. First, I'm going to have my abstract in Kurdish, and I don't know if it was a good luck or bad luck to be after me. I'm a Kurdish person. I was born in Kurdistan, Iran, and my parents have academic education. My mother was a teacher. My father has master of telecommunication engineering, something like that. And not every people are refugees. Okay. So while I am studying, I am reading that for you in Kurdish, I would like to ask you to pay attention to the English part. ام بابەتە باس لە کاریگەری گۆڕانکاری هەریمەکان لەسەر سووری ئاو و زۆربوونی تۆپەسەرەکیەکان وەک بارین و بۆ نەهاڵ دەکات. ئەمانە دەبنە هۆی زیادبوونی لافا و پشکەساڵی لە سەراسەری جیهاندا. بۆ چارەسەرکردنی ئەم گرفتە و بریاردانی پێویست زۆر گرنگە کە بایەخ بەڵێ کۆڵەمە و سەبارەت بە بەشە جۆر وا جۆرەکانی ئەم بابەتە بدرێت. Okay. I know that all of you are familiar with this first slide, but just as a warm-up, I want to briefly review some water cycle elements. Okay, water cycle elements or hydrologic cycle is describing water circulation around the world in its different phases as solid phases, liquid phases, and vapor phases. And we have learned its elements in elementary school, which is evaporation, condensation, precipitation, infiltration, and runoff. Another very short review is about climate change. We have studied, and I know everyone knows that, what is the difference between weather and climate. So sometimes we see in the news that a flood happened, and they say, oh, it's due to climate change. But weather, as we know, is a very short pattern that happens something between hours to weeks, and climate is something longer, up to millions of years. And we know that climate has its variable. We know that Earth has ice age and other patterns. So climate is changing. It inherently is changing. It has its variability. And the question is, we know that we have made many anthropogenic change to the climate, to the environment. We have done deforestation, we have emitted many CO2 to the earth, and we are considering about greenhouse concentration. Okay, so the question is, this climate change and this greenhouse gas concentration, how is going to impact the water cycle that we know? Okay, there are chain of reaction. Due to greenhouse gas concentration, we have more water to be evaporated, and as we have more evaporated water, we have more water to precipitate. So this will cause to intensification. water cycle. Water cycle is going around for millions of years, but our anthropogenic change is going to cause it to be more intensified. Right now, Dr. Hauser, which I would like to thank him for coming here, and part of his research team, we are working on a project funded by NASA. It's called Water Cycle Intensification Indicator. We want to measure the intensification of water cycle. And this intensification will cause more extreme hydrologic events, such as severe floods and severe droughts. Okay, if we want to make it in one picture, this is because of hydrologic intensification. Those areas which are wet is going to be more and more wet weather, and those areas which are dry are going to be more and more drier. And we experienced this in this winter in the United States. The East Coast has more severe winter, and at the meantime in the Western Coast we have very extreme floods, drought in California. Okay, another matter is stationarity. First, let's start what is stationarity and what is non-stationarity. In a simple word, stationarity is the assumption that what has happened in the past is gonna happen in the future. It is our basic assumption to simplify the problems of the stochastic change, the climate variability change, make it in a stationarity world and assume that what happened in 100 years is gonna happen for next 100 years. And we use it for designing our infrastructure hydrology. I will describe it more. But in 2008, hydrology community received a shocking wake-up article, which is called "Stationarity is Dead." This article, which got something like more than 1,000 citations by Neely, it's called that due to those climate change and anthropogenic change, stationarity is died. And this lead us to a non-stationarity world. And in this non-stationarity world, how we are going to design our infrastructure in this new world? It's a very critical question. Okay, what we have to do now? First, let's make a brief review. When we want to design a bridge or a dam or any infrastructure, especially for those who are facing water, you have to deal with nature. We have a historical record, normally by USGS and now by satellite data, from 100 years or 150 years. We analyze this and we are doing some statistical analysis to find the extreme event and the normal event to design our bridge and our dams. So we assume we have a estimated amount of flood that could happen. We calculate that, let's say we have 100 cubic meter flood. So this will cause something like, let's say, 10 meters of flood. Okay, then we make a safety factor and we design our bridge 12 meters for our dams. But this assumption was based on the stationarity world. Now we have changed lots of things to environment. So what will happen to that maximum flood? And the point is, if that flood overpass the bridge or the dams, they will collapse and there will be a big disaster for the economy. So there are some problems for predicting future, but this problem exists right now. How we are going to solve it and how we are going to adapt to this non-stationary world. First suggestion is making a bridge between civil engineers and climate scientists. Right now, we don't consider climate change in our building. In many of design, we cannot step any design or construction, and we have some problem with climate change. We need to make this bridge to understand the impact of climate change on the hydrologic cycle and considering these effects on the design of the infrastructure later. So maybe the final project we will review the building codes. But let's talk about the limitation. Right now there are some limitations. Climate models which are going to predict the future are not reliable right now. Sometimes they make totally negative prediction of the future. We have many climate models, climate satellite data, analysis, and all of them are having sort of different prediction of the future. And it's a problem. Another problem is when you are thinking about the whole globe, the whole Earth, we have to make a very huge computational space to predict, to make a good computer analysis. Sometimes we have to consider the impact of clouds, climate, and it's very complicated. So right now we have problem with our climate models. And another problem with the climate models of the models. Take a look at this normal distribution. We are familiar with it. Our climate models right now can make prediction of the means of this distribution. But they are very weak on the prediction of these tails. And what does this tails means? If it's a normal problem from normal distribution, this could mean extreme flood, and this side would mean extreme drought. Those extremes are the amount of flood that could destroy. So they are very critical, and we are not able to predict them very well. So right now, our models are not reliable. And on the other hand, extreme events are very important, and we cannot stop any construction. So what we should do now is the problem that we see extreme floods and extreme drought, and we are not ready to adapt to this world. So, as a conclusion, an interdisciplinary approach between scientists and civil engineering is the first step to adopt this non-stationary world, regardless of which political party are on the government. We should be able to have better water resource management and be prepared to adapt to the civil engineering, to this change in climate. So, the ongoing question right now is how we can live in the new non-stationary world, how we can adapt, how we should manage our water resources. Right now, Dr. Hauser, the team of scientists, has written a proposal for Department of Defense to just simulate these non-stationary scenarios for just 3 of their military base for something like $2 million. Another proposal by Dr. Hauser is non-stationarity and managing the sustainable management for George Mason is $1 million project. So they are very expensive and still cutting-edge research. And I am very honored to be here and work with Dr. Hauser as a member of his team. And we have wrote a proposal for NASA student fellowship based on non-stationarity. So it is very critical issue right now, and it's a big question in the hydrology community. Thank you for your time.